Hello. This talk is on distortion and metric matching with ordinal preferences. This is based on joint work with Nima, Anari, and Moses Charikar from Stanford University that was presented at EC 2023. So let me jump right in with a setup of the problem that we're interested in. Let's suppose that you have n agents and n items that lie in a metric space. So here the blue points represent the agents, the red points represent the items, and the metric space is just the two-dimensional plane. Our goal is to match the agents to the items in a way that minimizes the total distance of the pairs that we match. And so, for example, this would be a pretty good matching because all of the agents are matched to items that are quite close to them. And you can imagine that if you tried to make any serious changes, that the total distance of the pairs that we match would increase. On the other hand, this would be a much worse matching because the total distance is increasing because so many agents are matched to items that are much farther away from them now. So if the problem was just this, then it would just be the min-cost matching problem, and there wouldn't be much more to say about it. But there's a catch, and the catch is that we actually don't know the metric space. So instead, we get some partial information about it, which is specifically each agent's ranking of the items in order of distance. So for example, this agent here at the bottom might tell us that this is their favorite item, and then this is their second favorite item. This might be their third, and so on. And so the input to the problem actually looks something like this. Each agent is giving us a ranked preference order of the items. And all we know is that as we go further down that preference order, the items are getting further and further away from the corresponding agent. And based on that, we still want to output some kind of matching, but we can no longer really hope to actually minimize the total distance because we have only partial information. And so we hope to do something that's approximately good. So the question is, can we still find a pretty good matching? That's one that's within a small factor of the true optimum cost. And this approximation factor that we can achieve is often referred to in the literature as the distortion. Okay, so to summarize the problem one more time, our input is these agents' ranking of the items in order of distance. Our output is a matching between the agents and the items. The cost of a matching is the total distance between the pairs that we match. And the goal is that regardless of the underlying metric space, only knowing that the metric space is consistent with the preference orders that we got, we want that the cost of our matching that we output to be only a small factor worse than the true optimum. And the question is, what's the smallest factor that we can achieve? So what led us to be interested in this problem? So interestingly, part of our motivation is that there's actually been an explosion of work in this metric distortion framework on a different problem in voting theory. And so in that problem, rather than having agents and items, we have voters and candidates. And instead of trying to pick a matching, we're trying to select a candidate whose total distance to the voters is small. And so there is a long line of work that finally settled the distortion, the optimal distortion of deterministic rules to exactly 3. And there's also a nice series of works that has gotten the optimal distortion of randomized rules down to within 2.112 and 2.753. There's also some other nice work here at EC that's not specifically about just the randomized or deterministic rules, but on specific kinds of voting rules and also how this metric distortion interacts with other notions of distortion. And if you're interested in learning more about this line of work, I recommend this survey, Distortion and Social Choice Problems, the first 15 years and beyond. And so overall, I think that this line of work has been a pretty big success, not just because we've settled one of these questions and gotten almost there in settling another one of these questions, but rather that this has shown us that we have this new lens that can give us a deeper understanding of existing rules. And it's also a very nice mathematical framework within of itself motivates the creation of new voting rules. So with that in mind, I think it's very natural to apply this metric distortion lens to the matching problem. And our hope is that we'll get the same kind of effect, that it'll encourage the design of some novel matching mechanisms and also give us a deeper understanding of existing mechanisms. It's also quite natural to apply this metric distortion viewpoint to matching because a variety of real-life matching problems actually involve physical distances. So for example, in the school choice problem, you want to match students to schools that are close to where they live. You have the same kind of considerations when matching patients to doctors. Maybe you want to match students to dorm rooms so that they don't have to get too far they don't have to travel too far to get to their classes, and so on and so forth. But let me dig in just a little bit more on one of these examples, the school choice example, so that we can understand more details about how the different aspects of the model might interact with that particular application. So actually, in a school choice example, you might think at first that actually it's a bit of a bad fit. And that's because the locations of the students and the schools are actually known. So the schools, everybody of course knows where all of the schools are. And the school districts that have to make these matching decisions often know the addresses of the students. And so this aspect of the model where the metric space was unknown seemed really, really important. And so it seems like, why am I bringing this up as an example for this model in the first place? So the idea is that this model is going to offer a more robust guarantee that can account for a variety of uncertainties that we wouldn't otherwise be able to account for. So for example, what if the real distance is actually the total commute that a parent has to make to drop their child off at school and then go to work? It's possible that both are, 10 minutes away from home, but the total commute, if they're in opposite directions, might be 30 minutes. So in that case, the locations of the students might not actually be really known. The other thing is, what if you're willing to go a little bit further for a school that's a better fit? Maybe one that you think is more academically rigorous in a way that you're interested in, or maybe they have a specific kind of sports program that your child might be a good fit for. And so in that case, the physical distance might only be one dimension to a much more complicated space. And so the idea is that if you have a matching that works for any metric space, then you might be able to handle some of these kinds of uncertainties. And also, because metric spaces are so versatile and general, just having a guarantee that your matching has low cost with respect to any metric space is in of itself a very strong guarantee on the quality of a particular matching. But maybe the issue is that this is actually too good to be true. So maybe there are actually no low distortion mechanisms at all. And so I think this is kind of the key question that we have to answer. What is the optimal distortion that we can achieve? And then for a given application, we can decide whether that's too large for us to handle. Okay, so now what's known about the problem? So it turns out that we're not the first to work on this. But there's this nice paper in 2016 by Kargianis et al. And they studied two very well-known mechanisms called serial dictatorship and random serial dictatorship. So what do these do? These two mechanisms, they fix an ordering of the agents. And then in that order, each agent gets to take their favorite item that hasn't been taken yet. And so in serial dictatorship, this is just one deterministically fixed ordering, while in random serial dictatorship, this is a uniformly randomly chosen ordering. And so they showed that serial dictatorship has worst case distortion exactly 2 to the n-1. So they have both a matching upper and lower bound. And they also showed that random serial dictatorship has distortion at most n, and at least n to the 0.29. And so I think that this is quite an interesting new lens for understanding these two well-known mechanisms. I think it's quite natural to expect that serial dictatorship would be worse than random serial dictatorship in terms of fairness, because you're picking a random ordering rather than having an inherent bias. But to see this kind of exponential gap between these two, I think illustrates that point particularly well. So now what are our results? We have a series of results on this. So first, we give a new deterministic mechanism, which has distortion O of n squared. And so that kind of shows that you can actually get distortion comparable to random serial dictatorship, but without any need for randomness. And so this improves over the 2 to the n minus 1 distortion for a deterministic serial dictatorship. We also show a lower bound of omega log n that applies to all mechanisms, both randomized and deterministic. And so in particular, this shows that you can't get distortion that's a constant like we were able to in the voting setting. And so it's possible that for certain applications, this is already too much. And this shows that what we wanted might be too good to be true. We also show that if you're only interested in a near perfect matching, where 99% of the agents are matched rather than 100%, then you can get distortion of log squared n with a deterministic mechanism. And so this shows that if you have just a little bit of flexibility in your system, then you can actually get substantially improved results. Then we also show this exponential lower bound for a more general class of deterministic truthful mechanisms. And so this generalizes the lower bound that Kargianis et al. Showed for serial dictatorship. And it implies, for instance, for a natural way of adapting Gale-Shapley's deferred acceptance algorithm to this one-sided setting. Last, we show a kind of surprising connection between de-randomizing mechanisms and the asymmetric traveling salesman's problem. So actually, let me just say a quick few words about this in case you're interested. So what do we show exactly? What does it mean to de-randomize a mechanism for us? Well, we give a black box which can take in a randomized mechanism with distortion D and spits out a deterministic mechanism with distortion alpha D. So we have this kind of alpha blow-up factor in the distortion converting from randomized to deterministic mechanisms. And so this alpha, it turns out it's characterized by this thing that we call the thin matchings problem, which is exactly analogous to the thin trees problem, which was really important in getting improved approximation factors for ATSB. And so this was kind of a surprising connection. And I think that this thin matchings problem is a very simple and clean combinatorial question where probably understanding this problem better will be useful in a lot of different areas. And so we give an easy proof that you can get alpha at most n squared. And so already that's enough if you de-randomize random serial dictatorship to get distortion n cubed. And we conjecture that you should be able to get alpha at most polylog n. And so in that sense, we conjecture that the optimal distortion between deterministic mechanisms and randomized mechanisms shouldn't be too different, which might be surprising given the big difference between serial dictatorship and random serial dictatorship. Okay, so now I'm going to go into a little bit more detail about these first two results. So let's see how this deterministic mechanism works. So as a starting point, the idea is that wouldn't it be great if we could just give every agent their favorite item, because then we know that that's the optimal matching and we can't do any better. So let's imagine that we try to do this. So let's draw an edge here between each agent and their closest item. So the problem is pretty obvious, which is that we have matches that could collide. So we have these two pairs of agents who are matched to the same item. But there's a key observation that can help us, which is that if two agents collide, then they have to be close together in the metric space. And so the idea is to designate a representative among colliding agents. And then we can use their preferences as a proxy for the group. The idea here is that if representatives are close together in the metric space, then a good match for one is also a good match for the other one. And so you can just use one set of preferences as a proxy for the entire group. And so let's suppose that we designate these two agents to be the representatives. And so now we go back to trying to match the agents to the favorite items of the representative. So in each group, we have two agents. So we try to look at the top two items for the representatives. And then we still have this collision here. But the key thing is that this observation still holds true. And so what that means is that we can merge these three all into one group. and now operate as if this representative represents the whole group. And so now we look at the top 3 items for the representative, and then we reach a point where we don't have any collisions. And so at that point, we can arbitrarily match the agents in each group to the items that were matched to the representative. And so this is the rough idea for the mechanism. And it's not really too much more sophisticated than this. In fact, the proof only takes about 1 page. All right, so now a little bit about this lower bound. So the starting point for the lower bound is to imagine that we have 2 agents and 2 items, and the 2 agents have the same favorite item. So that's depicted in this picture here, where the metric space is just the distance on the graph. And so the 2 agents are closer to this item and then further from this item. And so because the 2 agents have the same preferences, we have to make some kind of arbitrary choice. We can't really distinguish between the 2 possible matchings. And so let's say that we have this matching. And so whenever we make these arbitrary choices, we can punish them with very biased metrics that are lopsided one way or the other. And so imagine that these were the true distances. So this agent on the right, it turns out they had a very strong preference. They were distance 0 to the closer item, and then distance 2 to the further item, whereas the other agent was actually completely impartial between the 2. And so it's kind of a waste to match the impartial agent to the better item. And this actually shows that you can't get distortion better than 3. So the optimum cost here would have been 1, whereas the cost of the matching that we picked was 3. But how do we extend this beyond 3? The key is to essentially iterate this idea. So this is 2 iterations up. And so essentially how a matching has to work on this instance is that the pairs of agents at the bottom compete for the items right above them. And then the winner gets those items, and then the losers then compete for the item further up. And this continues until some agent is stuck with the item farthest away from everybody. And so each time that we make these choices about who's the winner and who's the loser is a totally arbitrary choice. And so the idea is that we can punish those with some bias metrics, which look like this. And so it's just kind of a generalization of the previous example that we saw, where one agent, it turns out they have distance 1 to everybody. And it turns out that the optimal matching in this is also has cost 1. And so there are 2 key challenges to making this work. One is, how do you actually design these preferences so that they're consistent with all of these different metrics? So there would be 8 different metrics here that we have to have one set of preferences that is consistent with all of those. And in short, it turns out that by adding these exponentially increasing distances to the graph, and then looking at the preferences that we would get based on that, that's sufficient for getting what we want in terms of the preferences. The second challenge is, how do we match a given matching to a metric where it has high cost? And for that, I will leave that for you to look at the paper. And so let me conclude with just a couple of future directions. So after this work, this table gives us a state of the art for the upper and lower bounds for deterministic and randomized mechanisms. And you can see, even though we've brought the gap down substantially, there's still a huge gap between both the deterministic case and the randomized case. And so the key challenge is to try and close these gaps. Some particularly enticing first steps would be if one could find a mechanism with strongly sublinear distortion, like n to the 1 minus epsilon, or even square root n, which could possibly be achieved even by random serial dictatorship, because the lower bound is not tight. Another very intriguing question is whether there's a truthful mechanism with sub-exponential distortion. So our best truthful mechanism that's deterministic is still serial dictatorship. And so the question that's very natural is, can you do better with a truthful mechanism? Or is it possible that actually the same 2 to the n minus 1 lower bound essentially applies to every truthful mechanism? So with that, I'll conclude. Thank you very much for listening.